今後人類の未来は科学の発展と人類の精神的進化のバランスが取れて初めて安定したものになるであろうと確信をいたしております。この京都賞がこの両面の今後の発展に大きく寄与し、新しい哲学的パラダイムの構築を促進するいささかの刺激剤となればこの上なく幸せに思っております。
The Kyoto Prize is Japan's highest private award for lifetime achievement in the fields of advanced technology, basic sciences, and the arts and philosophy. Given by the Inamori Foundation, the Kyoto Prize is presented to individuals and groups worldwide who have contributed significantly to the betterment of mankind. The Inamori Foundation and UC San Diego share similar missions. We are both committed to scientific progress. We are both committed to cultural advancement. And we are both committed to solving complex issues through multidisciplinary research. World-renowned faculty from our two institutions have worked together across multiple disciplines to forward scientific discovery. Together, we are driving innovations in science, innovations in medicine, and innovations in technology.
Welcome, everyone. My name is Stephen Boggs. I'm the Dean of Physical Sciences at UC San Diego, and I'm very proud to introduce one of our most prolific faculty, Physics Professor Alison Coil. Professor Coil currently serves as the Associate Dean for Equity, Diversity, and Inclusion in the Division of Physical Sciences at UC San Diego. She holds the Ingrid and Joseph W. Hibben Chair in the Department of Physics. Professor Coil received her bachelor's degree in astrophysics from Princeton University and her PhD in astrophysics from UC Berkeley. She held a prestigious Hubble Fellowship at the University of Arizona before coming to UC San Diego as a professor of physics. Professor Coil is an observational astrophysicist, working with a focus on galaxy evolution, observational cosmology, and large-scale structure, making her the perfect host for today's discussion. We had the privilege of watching Professor Coil as she hosts a lively discussion with Professor James Gunn in honor of his receiving the prestigious 2019 Kyoto Prize in Basic Sciences. It is our pleasure to bring this rare opportunity to you. Please enjoy today's discussion.
It is my great honor to introduce Professor Jim Gunn, one of the Kyoto Prize laureates this year. Dr. Gunn is a very well-known astronomer. He is one of the godfathers of the field, in my opinion. Dr. Gunn was born in 1938 in Texas, and he has been interested in astronomy ever since his childhood. He was an undergraduate student at Rice University in Texas, where he was awarded a bachelor's degree in 1961. He was then a graduate student at the California Institute of Technology, or Caltech, which is in Pasadena, not too far from here in San Diego, where he was awarded a PhD in theoretical astrophysics in 1965. Dr. Gunn has had an enormous influence within the field of astronomy and astrophysics. Usually astronomers come in one of three varieties. The first is observers who use telescopes to observe the universe. The second is instrumentalists who build the telescopes and the cameras that are needed to take those observations. And the third kind is theorists who work on the theoretical understanding or interpretation of the observations of the universe. Dr. Gunn, amazingly, is all three of these, which is very, very, very rare. And he's had a deep impact in all three areas. He started building telescopes as a child with his father. As you can see in the presentation today, he built a very impressive telescope when he was in high school. And then as a graduate student, he switched and did foundational theoretical work. He predicted observational signatures that should be seen from very distant quasars or accreting supermassive black holes in distant galaxies. And specifically what he predicted is that the light from these very distant accreting black holes, as that light travels across space and time to us here on Earth, there's neutral hydrogen gas along the way that absorbs that light. That gas existed in the very early universe. This was what he predicted. Astronomers can use telescopes as time machines because light travels at a very fast speed, but it's a finite speed. It's not infinite. So it takes light time to travel through space. So by looking further out in space, you're literally looking back in time because the light had to leave those distant sources a long time ago to have had the time to travel to us here on Earth today. So we can learn about what the universe used to be like by looking further and further away and looking back in time. So the prediction that Dr. Gunn made as a graduate student about this light being absorbed as it traveled through space and time to Earth was not actually detected for decades later. And it was in fact the Sloan Digital Sky Survey, or SDSS as we call it, that Dr. Gunn conceptualized and helped build and run that finally detected this so-called Gunn-Peterson effect that he predicted should exist when he was a graduate student. I think it's worth noting that that theoretical work was done by 2 graduate students alone without the involvement of a professor, which is very rare. It must have been pretty obvious when Dr. Gunn was only a graduate student that he had a really bright future ahead of him. His graduate work alone was extremely impressive. Then Dr. Gunn moved to Princeton University and he effectively switched from doing theory to doing observations, because he was motivated to go and observe the ideas that he had put forward in his PhD thesis, which were just theory at that time. He wanted to go observe and actually trace what's called the large-scale structure of the universe. This entails observing galaxies on the very largest scales possible, essentially making maps of the 3-dimensional distribution of galaxies on scales of millions to billions of light years across. To do this, you need to observe many, many galaxies, not tens or hundreds or even thousands of galaxies, but hundreds of thousands of galaxies. And so that led Dr. Gunn to conceive and design the Sloan Digital Sky Survey. A key aspect of making that survey a reality was designing and building the hardware, meaning this huge digital camera that he designed and built, and also what we call a spectrograph. As Dr. Gunn describes in his talk, you can only learn so much about a galaxy from taking an image or a picture of it. And if instead you can take the light from that galaxy and pass it through a prism and disperse it or spread it out as a function of wavelength into what we call a spectrum, you get a lot more information about the galaxy. You can tell how far away it is, you can tell how quickly it's forming stars, you can understand the gas properties and the dust properties of the galaxy, you can identify supermassive black holes. There's a wealth of additional information in the spectrum that you don't get just from images alone. But at the time, the technology did not exist to obtain spectra of more than one galaxy at a time, until Sloan Digital Sky Survey and another survey called 2DF came along, and they used fibers to take spectra of many galaxies at once. Dr. Gunn explains this more in his talk, which you'll see in a minute. What this new technology allowed then was essentially for astronomy to move into the realm of data science, where now hundreds of thousands of galaxies could be observed at the same time, or samples could be built of hundreds of thousands of galaxies. And that allowed astronomers to run statistics on the full galaxy population, including mapping out this large-scale structure of the universe. So that paved the way for all kinds of new science to be done, beyond what Dr. Gunn has time to talk about in his talk. Astronomers used SDSS to study everything from stars and planets in our own galaxy to very distant galaxies, from accreting supermassive black holes to brown dwarfs. No previous astronomical survey had allowed that kind of immense scope of science that SDSS did. It was a real revolution in the field. Dr. Gunn has received numerous awards and honors, including a MacArthur Genius Award, the Gold Medal of the Royal Astronomical Society, the Gruber Cosmology Prize, and the National Medal of Science, among other awards. And Dr. Gunn is currently collaborating with astronomers in Japan and around the world to commission a brand new spectrograph at the Subaru Telescope on Mauna Kea in Hawaii. The new instrument is called the Prime Focus Spectrograph, and its aim is to take spectra again, but now of very distant galaxies, looking far out in space and back in time. He's still very active in research and is continuing to push the field in new directions to this day. I want to end with a personal anecdote. I was an undergraduate at Princeton back in the mid-90s, and I was there when the camera for the Sloan Digital Sky Survey was being built in a lab in the basement of Peyton Hall, which is the building where the astronomy department is. That building has two floors. The one floor is above ground, and that's where all the faculty have their offices. And then the other floor is in the basement below ground, and that's where all of the graduate students and undergraduate students were. And I remember at the time watching the faculty sort of scurry around the upper floor above ground. They were always rushing and busy, and they seemed deep in thought. They didn't seem, honestly, like the happiest people that I had ever met, but they seemed really intelligent and like they were working on very big, important problems. And I also remember seeing someone in the basement who was not a graduate student. He had a beard and a big smile, and he was building this camera for this new survey that they were doing. And I thought he was like a lab technician or an engineer. And in my memory, he has overalls on. I don't know if that's true, but I do remember him whistling all the time. And he just, to me, was clearly the happiest person in the whole building. And I learned later that that was Jim Gunn. I had no idea. I knew who he was, but I didn't know what he looked like. This was before the internet. You couldn't just look up pictures of people. And it never occurred to me that this really happy guy in the basement with a beard building this camera, working on hardware in this lab, was this world-renowned professor. But I think it just goes to show that if you're getting to work on realizing a lifelong dream, you're probably pretty happy. And also that nobody tells undergraduate students what's going on, because I had no idea. So with that, I give you Dr. Gunn talking about realizing his lifelong dreams.
I would like again to begin by thanking the Inamori Foundation and its founder for this prize and for the wonderful things it supports both in science and for the betterment of humanity. I'm very, very humbled and grateful that the Foundation finds me worthy of this great honor. And now I would like to tell you a little bit about my early life and career, a little bit about how the Sloan Digital Sky Survey got started, and a bit about what it has found about the universe. You saw in the introduction a picture of me with my father. I was born in 1938. My mother was a quite gifted artist, but who decided to give up art for raising me, and I'm grateful for that as well, of course. My father was a geologist, and he led a team during World War II to find oil, for looking at places where the Earth's gravity was slightly low, and that indicated that there might be a pocket of oil below, because oil is much less dense than rock. We moved around a lot as a kid, so I didn't really have a home. We would stay in a place about a year or so as my father moved from place to place. Because of the war, he had to become an expert machinist to keep his equipment up, and he taught me that skill, and that has stayed with me since. He died when I was 12 years old, and he was basically my friend. I had few friends because we moved around a lot. My teacher, my mentor, everything, and so it was quite bad. But I was interested in astronomy from the very beginning, really for as long as I can remember. I learned to read when I was fairly young, and the first book that I really remember, and certainly my favorite book, was a book called The Stars for Sam, which was written by a man, Maxwell Reed, for his nephew, a child. And he wrote a series of science books for children, and this book was published in 1938, the year I was born, and was a sort of major formative thing in my life. Once I read this book, I never really deviated very far from wanting to be an astronomer. I didn't have very much idea what astronomers actually did, of course, but I was interested in the stars, and I wanted to study the stars, and that stayed with me the rest of my life. My father was a geologist, but he was very interested in astronomy, and now he had a child to teach things, and so he had always wanted to build telescopes, and so we built little telescopes when I was a kid. And I was so taken by the subject that after he died, I continued to build telescopes. And when I was in high school in Texas, long after he died, I built this photographic telescope, which actually resulted in my first astronomical publications in about 1965. And so here is a picture of the telescope, there it is, the 8-inch telescope, and a photograph. It was an electronic drive, as the introduction said, and also had a camera. So I was able to take astronomical photographs, and I became very, very interested at that point in astronomical imaging and the state of the art in astronomical imaging. I was an undergraduate at Rice Institute in Texas. I majored in mathematics and physics. Did some research actually very early. This was in 1965. Computers were just coming along, were not used. They were used in business a fair amount, but were just beginning to be used in science. And I was lucky enough to get in at the very beginning of that and learned how to do scientific programming when I was yet an undergraduate. Graduate school, I went to Caltech in California. I wanted to do general relativity and went to Caltech to work with a man who died the summer before I arrived. So I was not able to work in general relativity, but became interested then I was still interested in observational astronomy, and was very interested in the universe in the large, and I became very interested in observational cosmology. That is, the cosmology is the subject of treating the universe as a whole, as an object, to try to understand how it expands and so on. I was very interested in Einstein and general relativity, and I did some work in gravitational lensing, which was quite important at the time. And also, about the time I was finishing graduate school, quasars were discovered. And it was thought that they were very, very far away. And I did some work with a fellow graduate student, Bruce Peterson, to look at the gas between the galaxies and the universe far away. And we were able to come up with an idea that you should or should not see this stuff, depending on exactly how it worked. And there came to be something called the Gunn-Peterson effect, which was not discovered for many, many years. And actually, it was the final thing was discovered by the SDSS much later, and we'll talk a little bit about that when we get there. While I was there, I continued to build instruments, both optical and electronics. And I became very interested in a particular aspect of cosmology, of the science of the universe, and that is how galaxies are distributed in space. Galaxies, as all things in the universe, gravitate, and so they pull on one another by gravity. And as a result, their distribution in space is not completely random, because where there are a few more, the gravity is a little higher, they pull and become even more. And so these clusters are one of the largest structures that we see in the universe. I did my thesis on this topic, and investigating something called the correlation function that says how much more probable, if you have a galaxy, is it that you have a neighbor than it would be if the galaxies were just strewn in space completely randomly. And this tells us a great deal about how the universe evolves and about how gravitation works on these very large scales. This is a picture, just a 2D picture, made from photographic data. This is of the southern sky, actually. So each dot in this picture is a galaxy. And you can see that the galaxies are not distributed randomly on the sky. You see clusters, you see groups, you see many, many things. All of this is the result of gravitation pulling galaxies together. This is simply a two-dimensional picture. If you add depth, and this was an early survey done at Harvard, the Harvard-Smithsonian survey, the depths are, the distances are color-coded, and so you can see that there's really very, very strong structure in 3 dimensions. And so I became very interested in making surveys that would do a better job. The statistics of galaxies in space, in order to do this well, is to do any statistical problem. If you're doing a sociological statistical problem, you have to have very large and very carefully chosen samples. And it's the same in doing statistical astronomy. Many astronomers spend their lives studying a few objects, a class of objects, sometimes only one object. And this is enormously important for giving us the depth of understanding in single things. But my emphasis was a little different. I wanted to study whole populations, to study the statistics, and to try to figure out, in the large, how the universe came to be the way it is today. This requires very, very large telescopes with very large fields, because if you want a big sample, you have to study a lot of sky, and that means you have to look at it, a lot of it at once. So you need very sort of wide field lenses in astronomy. And this is basically the story of my career for a very long time. 60 years ago, there wasn't very much in the way of surveys. There were small survey telescopes that made maps, partly for navigational reasons, partly just to find the locations of stars in the sky. But these surveys did not record very faint objects, and they didn't really allow quantitative interpretations of things, because it was just photography. Photography is beautiful, of course, to take pretty pictures, but it's very difficult to make quantitative measurements from. So all this changed actually began a long time ago, just as OLEDs began a long time ago before today. A fellow called Bernard Schmidt, who was a rather crazy Estonian optician, invented a camera that would make very, very wide fields on the sky, called the Schmidt camera or the Schmidt telescope. And there was a remarkable fellow called Fritz Zwicky at Caltech, who realized the enormous impact of this on doing surveys. And Zwicky was one of the people who really pushed the idea of doing surveys. And he pushed very hard for a project to image the whole northern sky. And this was done with a Big Schmidt camera that he persuaded people to build. And it ended in 1957. It resulted in a product called the Palomar Observatory Sky Survey, or the POS, which was photographs in red and blue light over the whole sky. He was a very interesting fellow. He's really one of my heroes in life. This is a picture of him, I think, in a kind of typical pose, and with the 18-inch Schmidt that he built. Zwicky didn't like astronomers very much. He thought all of his colleagues were fools, and there are many, many wonderful quotes from Zwicky, and this is, I think, one of the best of them. Astronomers are spherical bastards. No matter how you look at them, they are just bastards. But he is one of my heroes because of the emphasis on surveys. He also did really marvelous things early on. He predicted the supernova phenomenon. He predicted neutron stars. He knew that there was dark matter long before anyone else did. This is a picture of the 48-inch Schmidt that made the Palomar Sky Survey. So I want to step aside a minute from this general stream and talk about something which is very important for surveys. We have to have pictures, of course, to know where things are, but pictures don't tell us how far away things are. And in order to find out how far away things are, we need another tool. And the tool that we use is called spectroscopy. So let me spend just a few minutes talking about spectroscopy. One of the phenomena of light, of any kind of wave thing, is something called the Doppler shift. So if I have a galaxy that's moving, a star that's moving, anything that's moving, it compresses the waves, the light waves, in front of it in the way it's going. So the object is moving this way. You can see that this sphere of light was emitted when the object was back here, but the object has moved, and so the waves are compressed in the direction the object is moving, and they are stretched in the way the object is moving from. So if something is moving away from you, the wavelength of the light is longer, that's called, and its longer wavelength of light is red, that's called the red shift, and if it's moving towards you, the waves get closer together and moves to the blue, and that's called the blue shift, and we use this phenomenon to measure distances. The universe is expanding. We've known that for a long time, and what that means is that distant objects are moving away from us at very, very large speed. And the further away an object is, the faster it's moving, and there is a very simple formula that just says that the distance is some magic constant called the Hubble constant times the speed. And so if the speed is twice, the distance is twice. And that makes it very easy to sort things out in the universe. How do we do this? How do we measure the wavelength? Well, this is where spectroscopy comes in. We build an instrument which splits light into not just red, blue, and green, but into thousands of colors. And these individual colors tell us many, many things about the object, as we'll see. It makes a thing called a spectrum. The spectrum is just how much light there is at a given color of one of these thousands of colors. So the spectra of galaxies look like this. So here are three galaxies which are quite similar. This is the blue end of the spectrum, so this is blue light. That's red light. You can see that the objects at the top have a lot more red light. The objects at the bottom have a lot more blue light. You see several other things in here. Here you see a strong feature. That strong feature is repeated here, and it's repeated here, but it's at a slightly different place. That feature is the result of the absorption of light by calcium atoms. Well, that tells us something interesting, because it says that this galaxy, hundreds of millions of light years away, has calcium in it, the same calcium that we see on Earth. That feature is magnesium. That feature is sodium. So we see from these spectra what the object is made of. The fact that this one is shifted farther to the red than this means that it is receding from us more rapidly. That number is given by this redshift number here. We'll get back to that later. So this object is relatively nearby. This object is moving faster and is farther away. This object is moving faster yet and is even farther away. And so from this, we see what the objects are made out of, but we see more. This object is blue. This object is red. The blue comes from very young stars that were made only a few million years ago. This object has no stars that were made only a few million years ago. So these spectra tell us an enormous amount about the chemistry, about the history, and in fact, about the motion of these objects. So it tells us what the object is made of, how fast it's receding, and therefore how far away it is if it's out in the expanding universe. What are the temperatures of it? And also, if you think about it, the stars in these galaxies are in orbit about the center, and so some of them are approaching and some of them are receding. The result of that, there we go. The result of that is that if things are moving rapidly, these lines are broad, and if they're moving slowly, they're narrow. So we see not only how far away, how fast the thing is moving, but how fast things in it are moving with respect to one another. So we come back to surveys and how you do them. Photography it makes beautiful pictures, but it's not a quantitative method. And there was a lot of work, this kind of parallels what Dr. Tang told us about light emission. Astronomers don't need light emission. We need devices that record light. And there has been an enormous amount of work kind of paralleling, in a way, the work that he talked to you about light emission. Certainly photography would not have done this. We could not do a better survey with photography. We need new detectors. So in the 1970s, when I was at Caltech, Jim Westphal and I started working with a technology called CCDs that were developed at Bell Labs and that NASA were very interested in for space missions. We proposed and won a contract from NASA to build the camera, the first camera, for what was called just called Space Telescope then, that is now called Hubble. CCDs are very efficient, but at first, just as with the displays that Dr. Tang talked about, they were just too small. We needed bigger things. With the small CCDs, we built a camera called 4-shooter. This is a picture of the 4-shooter team on the 200-inch telescope at Palomar. The instrument is this big black thing in the background that you can hardly see. Here is Jim Westphal, my co-collaborator on Space Telescope, and a small team of people, of really excellent people, who built the instrument. So we needed something bigger. So in 1986, a fellow called Morley Blount that we had been working with at Texas Instruments moved to another company called Tektronix that was interested in making very big CCDs for things that didn't work out, but never mind, they made big CCDs. And Morley showed us this is a single silicon wafer, 100 millimeters in diameter, with a single device on it. And when I saw this, I knew that here was a way to do this wonderful survey that I had been wanting to do for most of my career. So let's build a camera, put a lot of these on one focal plane, and go from there. So this was the beginnings of the Sloan Digital Sky Survey. So I worked for a couple of years designing these things. I needed to design a new kind of telescope, actually, to use it. A big focal plane with many of these, many filters to obtain color data to get temperatures over as big a range as possible, and also to work on digital storage of the data, because if we had a lot of data and it was not available in digital form, it would not be very useful. But the survey would also not be very limited without spectra. But this big CCD was also a perfect device to serve as a detector for spectrographs. But if we want to do several objects at once, why would we want to do several objects at once? Well, When you break the light into all these thousands of colors, each color becomes very, very faint. And so it takes a very, very long exposure in order to record this spectrum. A picture, there are only a few colors, and the colors are still pretty bright, and it doesn't take very long. So it takes much longer to get spectra. Just as an illustration, to do what Sloan did, suppose you wanted to take the spectra one by one with the telescope. The exposures are of the order of an hour each. 1 million galaxies, 1 hour, that's 1 million hours. At a very good site, astronomical site, there are about 1,000 dark, clear hours per year. And with no overhead at all, but there's always overhead, just making things work, it takes 1,000 years to take 1 million spectra. And I don't think any of us were quite ready to wait 1,000 years. But if you can do 500 at once, it only takes 2 years to do this. So the planning began for what became the SDSS. We had just joined an observatory, a new observatory building in New Mexico. The site seemed quite good for this, and we rather slowly and with difficulty obtained funding for this with a very large gift from the beginning from a fellow on the board at Princeton. And so eventually, the people involved in the Sloan survey were these, and I would like to bring your attention to this, a very, very large lot of work in the Sky Survey was done by the Japan SDSS promotion group. So Japan has been our colleague in this for a very long time. Why did it start then? Well, it really couldn't have started earlier because the technology simply wasn't there. We had to have the big CCDs. We had to have high-efficiency optical fibers. I'll say more about fibers in a minute. That's how we get many spectra at once. And cheap and readily available computing to handle all these things. So the goals of the survey were to image the whole sky as 40,000 square degrees, and to look up out of the Milky Way galaxy into the sort of clear part of the sky was to image the 10,000 degrees in the north, to classify and measure all the objects we could take pictures of, which was many more than we could take spectra of, about 200 million, to measure the redshift distances to the brightest million galaxies and the brightest 100,000 quasars, and to put this data together in a database that people could use. This picture you've seen before. This is just the Princeton team, but there were many, many institutions. Here is me and my wife, Jill, who played a very important role in the software in this project, a couple of our Japanese colleagues, and many others sitting in this room. So this is the site. The new survey telescope is here. You've seen pictures of it before. A nice picture taken at sunset. This is a picture of the instruments at the telescope. The two big green things are the spectrograph, and the camera, which had 30 of these big CCDs, is in the center. This is a picture of the focal plane. There were 30 of these things, and they were arranged from red, green, two infrared, an ultraviolet filter and two infrared filters, so that we got, as a star went through this, we got data in all 5 colors in about 5 minutes. This is the distribution in the spectrum of the light from the ultraviolet, green, red, infrared, and farther infrared, and we recorded all of those basically simultaneously. Here is spectra. We did this by making a large aluminum plate, drilling holes at precisely the locations of galaxies that we learned from the imaging, plugging optical fibers in. The optical fibers come down, make the spectra, and go to the CCDs. You've seen this picture before. These are representative spectra from the survey. This is the sky that we covered, and you can see the dark is the main northern area. The green is a survey to look not at galaxies, but at stars. This was the data release at the end of the first phase of the survey. 8,000 square degrees, not quite 10,000, but we did the 10,000 in the next year. Photometry for several hundred million objects. Spectroscopy over 7,000 square degrees, 1.2 million spectra, and a lot of spectra of stars. So this is a kind of step through the survey. This is a picture with these bright things are put in by hand. They are the bright stars in the sky, just to sort of orient you on the sky. And what we're going to do is just zoom in, but we could zoom in to anywhere in this area, just as we're going to zoom in here. So we get closer. You can begin to see in the center maybe what we're heading for. This is called the Whirlpool Galaxy. So from that large area over the sky, one can focus and zoom in on any object you want in that large area. And there were many, many lovely objects we took pictures of. This is a picture of a globular cluster of a galaxy that is exploding currently. This stuff in the middle is not just a mist. It's gas being blown out of the center from a major explosion in the center. A beautiful spiral galaxy. A galaxy that has just suffered a collision with another galaxy. Galaxies don't always keep to themselves. They interact in very nasty ways with their neighbors. This is the nearest galaxy to us. This is Andromeda, the Andromeda spiral. And what I want to draw your attention to is this area. We're going to zoom in on it. This is just in one nearby galaxy. So we're getting closer. We're looking at a star formation region. This is gas, which is excited by hot stars in this galaxy. We come in. We also step way out in the universe. These are nearby clusters of galaxies. This is one in Coma, Hercules. And even farther, this group here is a group of galaxies at a redshift of about 0.3. That means about 30% of the way back toward the Big Bang in the system. And this is sort of at the limit. In this was just a single pass. We also did part of the sky, in which we did many, many times, so that we could add the pictures together. And you can barely see right in here anything, but clearly when we stack things together and make very long exposures, this is a cluster at about a redshift of 1, when the universe was about half its present age and half its present size. Lots of beautiful things in the Milky Way galaxy. These are all gas clouds in the galaxy in lovely colors. Now, this is the sort of 3D distribution. You saw the movie at the beginning. This is distance. So we're looking, this is just a thin slice of sky, looking at how the galaxies are arranged. And you can see that there are filaments, there are voids, there are clusters. It's a very complicated structure. How did this come to pass? Well, in 2001, this rocket was launched, which had a satellite, which made a map of the microwave sky. This is called the cosmic microwave background, the WMAP sky. The real distribution of this, it's almost completely uniform. The brightest things in here are about a part in 100,000 brighter than the coolest things here. But it is these little ripples in the early universe that made the structure we see. So we now know, and I really don't have time to go into how we know these things. The universe began 13.6 billion years ago. The universe is full of energy. And Einstein tells us that energy and mass are the same thing, in a way. And the things that we know about, protons and neutrons and electrons, is only about 4% of this. 25% is dark matter, and the other 70% is some dark energy that we don't quite understand. So let me say, if I go to a place where there is a very slight bump in the mass distribution, and follow it, what happens is this. This is a bump in everything, in the ordinary matter and the dark matter. There's a lot of pressure in the early universe. It's very hot. And that pressure pushes the ordinary matter out, but the dark matter doesn't feel this pressure. So you see the ordinary matter, which is only a small part, going out. And the universe is cooling at the same time, and it becomes cold. And what's left is around every place that there was a bump, a hill, in the early universe, there is an extra distribution of matter. Can we find that in this? Yes. If we count galaxies, going out from the distance from a big galaxy, this is the correlation function that we talked about, you see that it drops off very smoothly, but there's a hump. So there are slightly too many galaxies in this ring. And this tells us that we understand pretty well what is happening in the early universe. Something else the Sloan did, because we had spectra of 1 million galaxies, we could easily look at their distributions. I don't have time to go into this in any detail, but this is colors, brightnesses, sizes, all of these things we can look at and look at the relations between. Let me call your attention to this picture. This is color versus brightness. These are bright galaxies, these are red galaxies, and let's look at that in a little more detail. So what we found was that there was a red sequence. These are the galaxies that we looked at that were red and not forming many stars, red and dead, they're called. There is a kind of green valley that separates these, and these are the blue things that are making stars like mad, even today. And so we want to understand how this developed from the microwave background and also how it developed from what we saw. We also studied the chemistry of galaxies. Stars make all of the things we are, the carbon, the nitrogen, potassium, all of these things are made in stars. And galaxies hang on to that gas when the stars explode. The stars explode, and that's how these things get out. Big galaxies, because they have high gravity, can hang on to this stuff. Little galaxies, these are big galaxies, these are little galaxies, are not so good at hanging on to it. And so there is a strong range of chemistry with mass. So the results of the SDSS, I think the ones I'm proudest of are these. We study weak gravitational lensing. Gravitating objects bend light. And so you can study this, you can use this to detect directly masses in the universe, because you can look at how they bend light together. The baryon acoustic oscillations are what I showed you before, this pushing out of the ordinary matter. The properties of galaxies we saw. But also in the solar system, we discovered thousands of asteroids and looked at families of asteroids, chemical families, orbital families. We didn't really set out to explore the solar system, but we did. We found brown dwarf stars. These are objects which are between stars and planets. They don't burn thermonuclear fuel, and was thought for a very long time that they existed, and they were discovered actually before Sloan, but we found many, many of them and studied their properties. And of course, the large-scale structure of the universe. So the impact of this, as of the end of last summer, there were 10,000 scientific papers which used SDSS data. These papers were cited nearly 500,000 times. There were 1,000 papers with more than 100 citations, and 7 among the 100 most cited papers of all time. But it wasn't all we did. So there was also a very important legacy, I think, for the science. We insisted from the very beginning that the data would be made public very quickly, and we succeeded in doing that. And this resulted in the really natural growth of collaborations over the world using our data, both within the collaboration and without. And this openness is something that I hope it actually has become part of the sort of scientific sociology of astronomy, and it appears to be being a model for new projects. There was also citizen science. There was something called the Galaxy Zoo. We published a lot of pictures and asked the public to help us classify these things. We didn't even have any idea whether it would work, but within a day of the publication of this, we had 70,000 entries and over 150,000 people did this, worked on this as we went on. So that's sort of where we are and have been. The SDSS was finished some time ago. What do we want to do next? Well, it's very important to know that when we look out into the universe, we also look back in time. And so the universe is its own history book. If we can look out far enough, go faint enough to objects far away, we can study what the universe was like 1 billion years ago, 2 billion years ago, 10 billion years ago. And so the next step, I think, is to go out and be very faint. We know today that the universe actually is in its dotage, it's dying. This is a graph of the star formation in the universe, which is sort of the activity of things. This is a look back time, so this is now. If we look back 10 billion years, 10 times as many stars per unit time were being born as are born today. So the universe was an incredibly active, noisy place compared to the rather quiet times of today. So we'd like to do a survey like SDSS, but with much bigger telescopes, to go much fainter, to study things far enough away that we can read this history. And it's happening. Japan is making it happen. There's a beautiful camera with 114 even bigger CCDs than we used, called Hyper-Supreme Cam. Satoshi Miyazaki, who I hope is in the audience and is there, oversaw the building of this. This is a photograph taken at the commissioning of this instrument at the Subaru telescope. And the imaging part of the survey is underway and more than half complete. These are pictures of the instrument. It's very big. As you can see, here is a human being by comparison. This is the team that actually built the camera, and this is the focal plane with 114 CCDs in it. This is a picture that the telescope made. I think even on this screen it doesn't do justice, but you can see that there are very, very, very many galaxies. The galaxies almost overlap. So the faintest of these galaxies came at a time when the universe was only about 1/5 its present size and 1/5 of its present age. What about spectroscopy? Well, we have to have a spectroscopic component. We're working very hard on a spectrograph for Subaru that, again, will use fibers, this time many, many more fibers, 2,400 fibers, and it will reach ordinary galaxies out to the place where the universe was doing all of this really active stuff. And this instrument has been my focus for the past some years. I said the universe makes its own history book. It's hard to read because you have to go very faint. You have to have very sensitive instruments and go very deep in order for it to work. And we're doing our best to try to read this book. We, of course, I can't say that we're completely ignorant of it because surveys, small surveys, lots of work on smaller numbers of objects is going forward, of course, all over the world, but nothing like the size of the SDSS and nothing like the size of these surveys that we're talking about that Subaru is doing. So I would like to express my thanks not only to the Inamori Foundation for this enormous honor here, but also for the privilege of working with a very large and excellent group of Japanese astronomers since SDSS days. And now, I was part of running the SDSS, but they have taken over and are doing a very much better job with very big telescopes. I should also say, and I did not say really sufficiently, that you saw the list of institutions for the SDSS. I was project scientist for the SDSS, but the work I did was 1%, some tiny fraction. All of that work was done by my colleagues at these institutions, and especially wonderful for me was that the work was mostly done by my younger colleagues. So we old guys and gals who ran the survey, and we did a pretty good job, but the science was mostly done by the young colleagues, and they did a wonderful job. And that continues in the project today, and I am enormously proud of that. I was kind of the father of SDSS, but it was my children who did the work. So thank you all, and thanks especially to the Inamori Foundation.
Hi, Jim. It's really good to see you. I don't know when I saw you last, but it's been a while.
Yes, it's also wonderful to see you.
Well, I'm so glad you could take the time to talk to us today from your home in New Jersey. Thank you. I wanted to talk to you first a little bit about Sloan, and then I want to hear about what you're working on now. But if you don't mind, let's start with Sloan.
Sure.
Do you mind talking briefly about some of the challenges in making Sloan actually happen? I feel like when we as scientists talk to the public about what we do, they hear about our successes, we tend to give this very linear narrative after the fact of like, I had the idea, I took the data, it was really easy, and I learned some stuff. And it doesn't work that way. And I want people to hear about the reality. Like, what were a couple, just one or two examples of challenges or bumps along the way?
I'm afraid, Alison, that in the case of Sloan, the challenges were not particularly technical. I think we had the project pretty well under control, not perfectly, and I'll come to some of those things as well. But the big problem was that this was a big collaboration, and that's a new thing for astronomy, and was a new thing for astronomy, certainly not anymore. And, there was funding crisis after funding crisis. There were several months which we didn't know we were going to be able to pay people's paychecks the next month. And of course, we were terribly late, terribly over budget, because nobody had done this before. We didn't really have any idea how much it was going to cost. By the time the project was done, we were 5 times over the initial guess for the budget. And that's pretty laughable, you think, but we didn't know about this stuff, right? The original plans were for faculty and students to do all the programming. That was probably an incredibly silly idea to begin with, and it certainly turned out to be a silly idea in the end. But there were really no major technical problems. Don York and I worked very closely with the detectors. We knew were going to be hard because they had just been developed. Big CCDs were not something you could just go buy off the shelf. And so that required very, very close work with Tektronix. But because we were running so late everywhere else, it was not a thing that actually was a showstopper. But because there were so many institutions involved, and because this was such a new way to do things, that managing the project was more than a little like the old proverb of herding cats, right? And so keeping the costs down, we were way over anyway, but obviously we couldn't run over forever. Keeping the schedule under some kind of control were really the challenges. So, not any, I think these are not things that plague science in general, but they're things that plague big projects in science. And it was certainly so for us because we weren't nearly as organized as NASA, for example. NASA has problems, of course, not to say not, but we had really big problems.
Well, but I think that's I think that really shows how different this was. What you were doing was really revolutionary. This was not how astronomy was done.
Yeah, absolutely not. Absolutely not.
That's really interesting. I also want to hear, was there anything that was unexpected, not just in terms of how long it took, but for example, because I was not part of Sloan, but I was part of other surveys, and sometimes something happens that you just didn't foresee. Sometimes even in the data, you start looking through the data and you see something and you're like, what is this? Like, I don't even know what I'm looking at.
I think the big thing there was weak gravitational lensing, which of course is looking for very accurate shapes for very large numbers of objects. And so, we played around with the idea when we first started the survey, but nobody realized that our data would be more than good enough to do this. And it was the first time ever. And that was so surprising and so wonderfully satisfying. It was just a wonderful thing. There were actually lots of things like that. Of course, Sloan was designed as an extragalactic survey. We were going to look at the large structure of galaxies in the universe. And it was really, and we were going to look for for distant quasars. Now, what was the biggest problem looking for very distant quasars? You look for things with very strange colors. Well, what are the strangest colors things you find? Asteroids, because they move. It was not designed as a solar system experiment, but we found tens of thousands of asteroids. We were able to classify them by their chemistry, by their color. It was not supposed to be a solar system survey, but I think we pinned down the population of asteroids better than all the work that had been done before, because we covered the whole sky and we could do this. Because they moved, we knew exactly where they were. Brown dwarfs. So these are very, very cool stars with very, very red spectra because they're very cool. And the surveys that had been done before were done in the infrared. But the peculiar colors of these things, they have methane in their atmosphere. This is a star. You expect methane in a planet like Jupiter, but not on a star. And it made them actually brighter in our reddest bands in Sloan than they were in the infrared. So we were very much more capable of finding them and found many more than the infrared surveys. And so there were not really very many good spectra to begin with. And so people hadn't thought about this. It wasn't that it was such a surprise. So there were lots of things like that. Again, with science, people knew there were red galaxies that were not forming stars, big elliptical galaxies mostly. People knew there were little blue galaxies that were forming stars, but there was no idea of the sort of sequence of these things, the classification. And we had enough spectra almost immediately to see that this wasn't some mess. It was actually quite organized, right? And that, of course, led to many, many things, and people trying to figure out where the blue galaxies come from, how the blue galaxies get turned into the red galaxies, which is, of course, still a major, major problem in the field. But there weren't data to say what you should be trying to explain before Sloan came along. So all of these things were just enormously gratifying. I think the biggest gratification for me anyway was the weak lensing, because we had no idea that our data would be of high enough quality to do this. But it was.
Yeah, I wouldn't, if you had asked me, I wouldn't have thought that the imaging would be high enough quality. So I'm not surprised that didn't occur to people.
Because we sort of knew all the warts there were, right?
Yeah, exactly.
Keeping the machine from working properly.
Yeah. So this gets at another question that I had, which was this survey, as you're just describing, it was so relevant for so many subfields in astronomy. It was the broadest scientific survey that had ever been done. Did you know at the time, did you have an inkling that what you were doing was essentially ushering in this paradigm shift of how we did astronomy to these big surveys?
I think we hoped. It was clear that there was a lot of sort of sociology involved in the beginning, and there were several institutions in the survey who said, let's measure galaxies down to the limit that we can take spectra for. So we sort of know what we're taking spectra of and nothing else matters. And we said, no. The data are capable of very, very much more than this. The idea, my push was that we would be limited by the statistics of the incoming data, no matter what. We wanted to be photon limited. We wanted to be able to get all the information that we could from the data. And we pushed very, very hard, and we're perhaps not completely successful at this, but we were not willing to give up, just to satisfy some requirements somewhere that somebody had written down. That paid off just so enormously. You know, the galaxy spectra were very good. Nobody thought we could do galaxy spectra of this quality with a telescope this small. I knew we could because we had designed the spectrographs and I knew what they were capable of doing, right? So I think the push for quality, which was not universal, I must say, but they just paid off so enormously.
That makes a lot of sense. And that's really smart. I've been in surveys where that wasn't the push. The push was just get a redshift.
The push was to satisfy the requirements, right? And so you design the machine and it's clear that the machine can do a lot more than the requirements. And so you just push like hell to get it done. Right.
That's so interesting. Yeah, and you also touched on something that I wanted to ask you about as well. Your career has spanned so much change in astronomy. I mean, much of which you led, right. But in terms of how we do astronomy, this current era of these really large surveys with these enormous collaborations that aren't just multiple institutions, but multiple countries spanning all the time zones, essentially. What has it been like for you from graduate school to now, watching the field go through all of these huge changes?
It's been just wonderful, Alison, right? When I started this, when did I get my PhD? In 1965.
Yeah.
You know, we didn't know how big the universe was or how old the universe was to a factor of 2. And people are now talking about percent kind of accuracy. And to see that develop has just been incredibly wonderful. You know, the whole, the cold dark matter model, the paradigm, we understand so much more now than we did. And I stressed in a couple of biographical articles that I wrote, and and it doesn't make everybody very happy, that the reason for this clearly is technology. We're not any smarter today than we were in 1950, but we have these absolutely wonderful tools that mostly we didn't develop. You know, they've come our way from the military, from commercial applications and things, and we are very much the beneficiary. And we've used them, I think, quite intelligently. But it isn't our doing entirely, right? It's tools that we've been delivered.
Yeah. And can you talk a little bit about the changes in how we do science? Because it used to be that papers would commonly have 2, 3, maybe 5 authors.
Yes. No, that's that's something else that I'm actually quite proud of. I mean, it had started well before we started Sloan, but you know, I was on the Palomar staff. It was not an open telescope. There were only a few of us who could get time. And you would go and you would get your 3 or 4 nights. And maybe you had a friend that you would work on with a paper, but most of the papers were either single or 2 or 3 authors. Now that was, of course, not true in physics. Physics had these huge papers with big collaborations. And there was some of that already happening with NASA, with IRS and other things. But of course, we didn't have NASA kind of money. And so I would have to go back and try to remember. We certainly, when we started Sloan, did not recognize the advantage of having lots and lots of people. We had lots of institutions because that was the only way we could get the money, right? But as soon, actually even before the data started rolling in, it was clear that there was a richness which was simply absent from just having a few people, because you had expertise that spanned an enormous range of things. You had people thinking about things, it sort of limited one brain. And we had to, it was a collaboration. We had to collaborate. We had to be on our toes. And as soon as the science started, it just flew up. And it was just fantastic. So and something I'm particularly proud of there is that we pushed very hard for Sloan to be very open. There were large NASA collaborations, but this group did that, this group did that, this group did that, and you couldn't sort of wander outside your box. And we recognized very quickly that that was not the way to run a big project. The way to run a big project was to let people do anything they wanted, to arrange whatever sort of sub-collaborations in the collaboration they want. And so I think both the big projects and the openness that I think I would like to take some credit for there has just enormously benefited the field.
Yeah.
But things were happening too, you know, there were women, many more women in the field. It was the sort of kings, the de Vaucouleurs, the Sandages, they just weren't there anymore. And so the science could be very open and very free. And I just think we've benefited enormously from that.
Yeah, no, Jim, I think you're right. And I think that not being part of Sloan, being on the outside of it, I watched this from the outside, and I do think that it's really shifted the culture now to where there's a much greater push for all surveys now for the data to be public, to bring in all kinds of expertise, and even when there is proprietary data, to release it eventually. Like, I'm still using Sloan data in papers right now.
Or Alison, it's far from, you know, its content is far from exhausted scientifically.
Absolutely. Yeah.
Right.
Yeah. And it's been really interesting watching the change in the field to now to get funding for a new survey. It can't be about one or two science topics. It needs to be very broad because of Sloan and what Sloan did.
Right.
I want to talk about what you're working on now, because it's not like you've been resting on your laurels. So I've been hearing about this prime focus spectrograph for many years now. And I wanted to ask about, I think it's being commissioned right now. What's the status of it?
So the status, let me describe the instrument first a little bit. So this is a big spectrograph to look at faint galaxies and quasars again, sort of Sloan, but much fainter, to try to go out far enough in the universe that you can see the evolution in front of your eyes, which we couldn't do with Sloan. It was too shallow. So it's 4 big spectrographs, which are stationary and are fed by a long fiber. It's 50 meters or so of fiber. And there is a machine at the prime focus at the top of Subaru with 2,400 little robots that position the fibers. So again, it's there was is still going on actually, and a survey to do imaging on Subaru with a very big camera called Hypersuprime Cam. And so, you know, we imaged in Sloan, found the targets that we're going to do spectroscopy. So I think they're doing exactly the same thing, except going much fainter. So this spectrograph has these 2,400 little robots at prime focus that are feeding fibers down to 4 big fixed spectrographs that live in the dome. And we will go about a factor of 20 to 30 fainter than Sloan was able to go. And we will try to go even fainter than that, although whether we will succeed or not is not completely clear. But it's a fiber spectrograph fed by fibers. 4 2,400 objects at one time, which is many more than Sloan was able to do. The 2,400 fibers are divided into 4 bundles to feed 4 identical spectrographs when it gets there. And the science we want to do is a kind of, the thing that I'm primarily interested in, of course, since I did Sloan, was a Sloan-like survey, except in, you know, you go out so far when the universe was 3 billion years ago, 6 billion years ago, 10 billion years ago. So we do a little, not nearly as big a survey as Sloan, but Sloan-like surveys as the universe aged, to see how the galaxy population evolves a little bit, about how they form, how they merge, all of these things that are on people's minds today. There is also a survey going on to try to pin down the cosmological parameters again. In particular, the question of how the accelerating universe accelerates because we don't understand what makes it accelerate. We don't understand how that force, whatever it is, behaves over time, whether it's constant. And so there will be a big survey to do that. Also a survey on stars in the galaxy to try to look at chemistry of stars. We can go way, way, way out, away far from the galaxy to try to find out where the heavy elements came from, how they evolved as the galaxy formed, because we know, I think without any doubt, that we are an agglomeration of many smaller things. And we want to understand that process better. The idea for this project has been around for a very long time. And the National Science Foundation set up some studies for a spectrograph called WIFMOS that you probably remember. And the idea was to build a spectrograph like this. And so late in the game, the US woke up to the rather uncomfortable fact that they didn't have a suitable telescope to put this on. And so they began courting the Japanese because the only big telescope that had a big enough field for this thing was Subaru, the Japanese National Telescope. This was going on, and the way the sort of scientific politics work in Japan is that there's a big meeting of all the Subaru users every year. But this is all sort of organized before, because it's very uncomfortable for the Japanese to have a contentious meeting because they're incredibly polite. The society is incredibly polite. So it all has to be decided before the meeting, and that vote in the meeting is just everybody yay, right? So they did all this homework. They came to the meeting, and just after it was announced, just after they had the vote, it was okay, the NSF called and said that WIFMOS had been canceled. And I don't know whether you can imagine what this does to the Japanese psyche, but it was a very, 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 very bad thing.
Yeah.
So there it sat for a while until the crash. And then the Japanese government decided to put a very large amount of money into science. And the Japanese, meanwhile, had been thinking about how cool this spectrograph, how cool it would be to have this spectrograph on Subaru. So they started a project of their own. There was not a lot of expertise in Japan about spectrographs. There was also, the funding was much better at the beginning. A new government came in and they cut things way back. So the Japanese needed some money. They needed some international partners, and they also needed some help. And so that's how it began. And so in 2012, something like that, anyway, a long time ago. And so we started, got the instrument designed, and it took 3 or 4 years. Some rather fancy optics, all of this stuff about the fibers, which was, a lot of it was inherited from WIFMOS, because the WIFMOS teams were, of course, had developed this and they were interested in doing it. So there was a team from Brazil who was doing the fibers, a team from France who is doing the spectrographs. Johns Hopkins and Princeton are doing the detectors and the infrared and all the cryostats, the cold boxes that the detectors go in. The robots were developed at JPL and Caltech. But the sort of fancy thing that lives up at the top of the telescope that holds these things is being done by Asia and Taiwan. So it really is, you know, a thing that spans the world, and trying to arrange phone cons when it's, you know, when it's midnight in France and dawn somewhere else. But we manage, and one of the main reasons we manage is that our Japanese colleagues, when the project is being run from Japan, are just infinitely nice and infinitely flexible. And so they're generally the ones who are up at 2 or 3 in the morning or at midnight or so. And so they try to make it easy on the rest of us. But it has been a wonderful and incredibly happy project. It's very big, and like all these projects, you know, we're strapped for cash. We're just barely making it. Sloan was quite contentious because there were universities, there were government labs.
No, there was like a culture clash. I remember hearing about this. I mean, yeah, you're bringing together people from different backgrounds and cultures and forcing them to work together.
Culture is entirely right, and you know it. The universities are used to developing things sort of, you know, you solve things as they come. The government labs want everything written down in solid requirements documents before you do anything.
Yeah.
And you know, it was just wasn't very nice a lot of the time. Once I will say that once the data started coming in, everybody was so ecstatically happy because the data were so good that all of this went away. So it was almost entirely during the construction, but it was not happy. There's a book you may know by Annie Finkbeiner called I think a Great and Glorious, some completely ostentatious title about Sloan, and there's a lot of this controversy in it. It makes for a fairly interesting reading.
But the new spectrograph has been relatively smooth.
Oh, it's no, I mean, there have been lots and lots of technical problems, many more than there were with Sloan, because what we're trying to do is very hard. Yeah. But essentially no conflict.
Amazing.
And it's just been fantastic. Yes. Yes.
What's one of the first science papers that you're really looking forward to from this instrument?
Well, it's hard to say, actually, because as you know, since you're involved in this, there is a lot of work going on galaxy evolution outside this survey. And so what will come from it, I think, is a much more structured picture, just as has emerged from Sloan. But exactly, you know, what it's going to be, I really don't quite know. Mm-hmm. And of course, the whole cosmology thing at this point is just dotting I's and crossing T's and getting something a little bit more accurate. And people are hoping, because that's the way people are, that it will break our current model, and then people will go and scramble and figure out what's wrong. If it turns out to be that it completely supports lambda CDM, the current, then it won't be so exciting.
Right.
So I don't know. It's hard to say.
Well, I'll tell you something that I'm really looking forward to about it, which is, I don't know that this was something that was part of the initial scope, though maybe it was, but you'll be able to trace the circumgalactic medium with much better statistics than we can right now, because the survey is just so large. So I'm really looking forward to the circumgalactic medium results personally.
Yes, no, I think that's going to be important, but do remember that this is a fiber spectrograph like Sloan, and so you get what you get, you know, just in one place. You don't have a sort of spectroscopic picture.
Oh, I know, but statistically, you'll be able to build up a really detailed picture, I think, of the.
I hope so. Yes, just from the line. So that's going to be very good.
And so the spectrograph's being commissioned this spring, is that right? Okay,
so the current state is that there is a spectrograph at the mountain with a currently broken shutter. Oh, no. But the clean room has a currently broken crane. And so, you know, it's these little things that sort of keep you from going on. I have been working for the last 6 months on a tiny instrument that mounts to the Subaru telescope that feeds our spectrograph. It's called SUNS, the Subaru Night Sky Spectrograph. And it's a 1.5-inch telescope mounted on this 8-meter telescope. And it's just to get sky spectra. Mm-hmm. One of the biggest problem that we will face is subtracting the sky. Yep. And so we can get perfectly good sky spectra with a much, much smaller telescope. And furthermore, it's mounted to the telescope and it can work all the time when people are doing other things. Whenever the telescope is pointed at the sky and working, we can get sky spectra. So we just got first light on it. With the spectrograph with a broken shutter. There are 2 shutters, so only one of them is broken. And that seems to be going quite well. So it will give us a bit of a head start because the software development to do that. The objects we're looking at are typically 5% as bright as the sky. And you have to subtract very accurately to get accurate spectra.
Yeah.
And people have learned how to do this with slit spectrographs on Keck, but it's still, with fibers, it's still very, very hard.
Yeah, no, I hadn't heard about that other small instrument. That's really smart. That makes a lot of sense.
Yeah, I'm quite proud of having the idea. So
good job. Well, I think it's really, really impressive that you're still pushing the field forward in new ways. You're giving the rest of us a lot to work towards in our careers.
I'm an old man, but as soon as I can't think, I'm not really interested in going on. So I certainly hope to die with my boots on. So.
Oh, you're still holding the whole field. Don't worry about it. Well, thank you so much for taking the time. This has been really, really fun. And thanks for updating us on
so much fun.
info.
Yeah, thank you.
It's been really good to see you.
Really good to see you too. So take care, everybody.
今後人類の未来は科学の発展と人類の精神的進化のバランスが取れて初めて安定したものになるであろうと確信をいたしております。この京都賞がこの両面の本語の発展に大きく寄与し、新しい哲学的パラダイムの構築を促進するいささかの刺激剤となればこの上なく幸せに思っております。